It's our pleasure to have Oded Carmon from the Weizmann Institute, and he'll be talking about preparation and point counting in sharply o-minimal structures.
Thank you, and thank you for the invitation. So yeah, what I'm going to talk about today is joint work in progress with Binyamini and Dmitry Novikov. And if you were here for yesterday's talk, there'll be some slight overlap, at least in the start. So whether that's unfortunate or fortunate, I leave to you to decide. Okay, so just before I start, in general, what I want to talk about today. So I'll start with some motivation and setup, recall some notations and definitions that we need. And in particular, I'll review this notion of sharp o-minimality. And then I'll talk about two things called preparation theorems. So I have two kinds. The first will be called S preparation, which you can think stands for sub-analytic. And the second will be this thing called LE preparation, where LE stands for logarithmic exponential. And then at the end, I want to talk about two applications of these theorems. One of them is a sharp quantifier elimination result in certain structures, and also an application to point counting. So just starting at the end, before we record the definitions, I want to mention two special cases of our results, which I think are independently interesting. So the first of these is we show that the structure Rx is sharply o-minimal, and I'll recall the definition. And the second of these is that we get Wilkie's conjecture for Rx. Okay, now actually this Wilkie's conjecture for Rx was recently established by other methods by Binyamini Novikov and Benizak, but our method yields somewhat stronger formulation of this, and I will explain when we get there. Okay, so what is sort of the basic setup we want in these point counting theorems, for example, in this Wilkie theorem. So I need to recall some definitions. So the first of it is I have some set A in Rn, and I write A alg for its algebraic part. So this is the union of all positive dimensional connected semi-algebraic subsets of A. And the complement of the set, like, denoted the transcendental part, so A trans. What we want to do is we want to look at sets definable in, say, o-minimal structures and count how many rational points there are in the set up to some bounded height. So I have this notation here. So for a set A and some bound on the height h, I write AQH for all rational points in A that have height at most. What is the sort of classical statement? So I'll fix from now on some o-minimal structure S, and for me this always means over the set of actually real numbers, and the field operations are definable. For a set definable, a set X definable in such a structure S, the statement is that the number of rational points up to some height outside the algebraic part grows asymptotically slower than any power of h. So for any epsilon, we have some constant which depends on epsilon and depends on the set, but doesn't depend on h, and we have this sort of height. And it's known in general that this can't be qualitatively improved beyond the sort of h to the epsilon in the generality of general o-minimal structures. But in the same paper, Wilkie conjectured that maybe in special cases, in structures where we have a better understanding of the definable sets or have some more control over them, maybe we can say more. And in particular, he conjectured that in Rx, we can improve these sub-polynomial bounds to polylogarithmic ones. Okay, sort of, this was also mentioned yesterday, but if you want to try to sort of think how to attack this sort of problem, and you look at the proof of the probability theorem, so the key step there is really some sort of interpolation result. You have your definable set, you have all the rational points you're interested in, and what you can manage to do is to cover them by the zero sets of about h to the epsilon non-zero polynomials of some bounded degree. And this degree is roughly polynomial in 1 over epsilon.
May I ask one question? Please, bad examples which exist in which dimension we were constructed? was.
I think even one dimension.
Yeah, curve.
So in the lowest dimension.
Analytic
that's-
curve.
Yeah.
Yeah, curve in R2,
Yeah.
right? I mean, Jonathan's answer paper.
Yeah, so I mean, here it's really sort of important that the polynomials we use are of bounded degree because it's all formulated in terms of definable families and an o-minimal structure. And if you want to have a definable family as a polynomials, it has to have a bounded degree. But if we could, for example, put in an unbounded degree, we could try and plug in, let's say, a degree that's for epsilon, we would take something like 1 over log h. The degree would be about poly log h. And then, yeah, put in 1 over log h here in epsilon would kill this h to the epsilon term, and we'll be left only with c. Of course, now the c won't be constant anymore. It will depend on epsilon. And then another thing we have to do is try to analyze the dependence of this constant c on epsilon as epsilon goes to 0. Okay, and these sorts of considerations is trying to work with maybe polynomials of unbounded degree that don't fit in a definable family and trying to analyze the behavior of these constants is sort of what was the motivation for this notion of sharp o-minimal structures. So just review the definition. What is the sort of data we need? We have a fixed structure S, and now we want to assign a measure of complexity to sets definable in the structure. So we want to associate some numbers to each set, measuring their complexity. So this is something we call a format degree filtration and FD filtration. And it's the following data. It's a sequence of sub-collections of definable sets satisfying some properties. So this first bullet point is just saying that each one of these SFDs is a collection of definable sets. And conversely, any definable set lies in at least one of these SFDs. So it has some format and it has some degree. The second point is just saying that this is a double filtration in the sense that if I have some set and it has format f and degree d, then okay, it also has format f plus 1 and degree d, and it also has format f and degree d plus 1. So you can think of this as saying like the format is worst f and the degree is at worst d. You can't really give it an exact, just an optimal pair of numbers. And in general, this notion of format is somehow supposed to be analogous to the ambient dimension. So we also impose that if a set has some definable set in R to the n and it has some format, then this format has to be at least the ambient dimension. So far, this is just very general. You can put this on any collection of sets S. It doesn't really use the fact that it's a structure. So we need to impose some compatibility axioms between this sort of object and first order construction of definable sets. Okay, so the terminology here is that we say that a filtration like this is sharply generated by the structure if it satisfies the following. So let's say I have some finite collection of sets in R to the n, and they each have some format and degree. So each set AI has format Fi and degree Di. So if I take one of these sets and I take its complement in Rn, or I project it onto its first coordinates, this doesn't change the complexity. If I sort of add a variable, if I take a Cartesian product with R on the left or on the right, this increases the format by 1, but doesn't change the degree. If I do any Boolean combination, I take intersections or unions, the format of what I get is the maximum of the formats I started with, and the degree is the sum of the degrees I started with. And most importantly, the point of this whole thing is to sort of track the interaction with algebraic varieties and with intersections with algebraic varieties. So if I have some polynomial in n variables, then its zero set will have format n, and the degree would be the actual degree of the polynomial. Okay, so when we have such a structure and some sharply generated FD filtration on it, we'll say that they're sharply o-minimal if they satisfy a finiteness axiom. So this is like a quantitative version of the axiom of o-minimality. So what is the requirement? For every definable subset of R, it has some format F and degree D. Then the number of connected components of the set is bounded by some polynomial in D, and the choice of this polynomial depends only on the format. And this collection of polynomials is part of the data defined in the structure. So I need a filtration and I need a collection of polynomials satisfying this sort of property. Okay. In that case, we'll say the structure is sharp, and I'll abbreviate it with this little sharp sign. Okay, so just about the definitions, any questions? Okay, so really, there's some history about partial results about Wilkie's conjecture, but in this formalism was used in its eventual resolution very recently by Dmitry and Benny, and they did it sort of in two steps. So there was a sort of restricted step and then an unrestricted step. So what do I mean by that? First, they showed a sort of this polylog Wilkie estimates for the structure of restricted Pfaffian functions. So this in particular includes the restricted exponential. And yeah, the form is a bit stronger than in the original conjecture, because here you have some better understanding of the polynomials. Instead of just some polynomial depending on the set X, it's a polynomial that depends only on the format of X, and it's also, the bound is also polynomial in the degree of X. And then from this restricted result, they upgraded to the unrestricted exponential, but there they have to use some kind of ineffective property of the structure Rx that doesn't reduce from this unrestricted case back to the restricted case, but here there's no sort of, it's not clear how to get something more specific than just a polynomial depending on the set X.
But it's actually a formal deduction from the previous theorem, or
you have to do some reduction. So what this model completeness says is that any set definable in Rx, you can think of it as a projection of some quantified preset and some maybe higher dimension. And there, because you only want to count points up to some height, it's enough to take a restriction of such a set, intercept it with a large box, and then this brings you back into the restricted setting. But I mean, you don't know sort of from which dimension you project it down from, and so it's hard to say specifically what is this polynomial.
Yeah, the problem is that this model completeness theorem of Wilkie, it's a deep result and it's not effective. We're using that along the way, so we lose this.
but you're not going through the proof again, you're recording this.
So in that sense, if you have this as a black box, you can just deduce this. Yeah. Okay, so really this restricted part wasn't formulated specifically for restricted Pfaffians. It's formulated with some slightly more general context, but it needs some extra assumptions. So it's not enough to work in some sharply or minimal structure. The proof legally uses the fact that the structure of restricted Pfaffian functions has some extra technical property. It's called sharp derivatives. And this controls how complex iterative derivatives of definable functions get. So it's saying something like the format doesn't increase too much when you take iterative derivatives. Okay, and this sort of property, it holds for restricted Pfaffian functions or Pfaffian functions, but it's we sort of think it's not reasonable to expect for this to hold in maybe some other examples of sharply or minimal structures that we expect to arise in applications. And part of the motivation of this project was to try and get another proof of Wilkie's conjecture, but now maybe using some other assumption that we believe generalizes more readily in other conjectural structures. And the sort of philosophy is that we're going to trade this control on high derivatives by holomorphic continuations to large enough domains. And this is sort of the idea. So I won't give a precise definition, but this is an imprecise one for us to work with. So I'm going to fix a sharply or minimal structure S with some filtration SFD on it from now on. And I'll say it's analytically generated if arises in the following way. I look at the collection of all holomorphic functions which are definable in the structure, whose domains are roughly products of disks and annuli in complex space. And if this collection of functions and their sort of assigned complexities together generate the original structure and the filtration I'm working with, then I'll say this structure is analytically generated. What this sort of gives us is that if you work in such a structure and you start with a real function, which is definable and it has complexity, then we know that it continues holomorphically to some suitable large domain, and this continuation is definable, and you can control the complexity of this continuation. And this is really what we use. And just as an example to keep in mind for such a structure, you can think of this structure of, it's called restricted elementary functions. This is just what you get when you take R and you add restricted sign and restricted X. Because each one of these, when restricted, is Pfaffian, this thing is a substructure of R Pfaff, and so it is sharp. Okay.
Sorry, like you're including the format degree stuff in this data? Like
Yeah, so let's say I start with R Pfaff, and it has its own sharp filtration, and then I look only at the sets in this substructure, and with the same format and degree filtration. And then I close off under the axioms of sharp o-minimality, I get some substructure. Maybe now the sets won't have exactly the same complexities in the original one. But yeah, I start with some given collection of sets and complexities, and then I close off under the axioms. And whatever I get, that's the structure I work with.
Wait, what do you mean that you close by the axioms? Why can't you just intersect the filtration from the higher one with the sets definable in the smaller one?
So maybe I have a set that's definable here, and it might have some low complexity in this larger structure, but that comes from some way that I can construct this set using sets that are only in the larger structure. So what I want is really to start with some complexities of my actual building blocks, and then only say that a set has low complexity if it can be obtained from these building blocks in a short sequence of steps according to these axioms about what happens when you intersect or add a variable. Or
but the fact that the bigger structure is sharply o-minimal.
Yeah, this implies that this one.
That implies that. Okay.
Yeah. If I have some. Yeah.
Maybe just a comment, this will happen. So if you take, let's say, the graph of the exponential only on the real line, but a very long interval, then these all have a bounded format, no matter how long the interval is. It's all of bounded format in degree as a restricted Pfaffian function. But if you try to write it from holomorphic things, you will kind of need more and more, because the analytic attenuation of E, it's not definable on a big, if you just took a big polydisc, for example, it wouldn't work, because then E is periodic in that. So you really will have to cover it by a lot of small polydiscs. Yeah, so it's it's a phenomenon that actually happens.
Okay, so yeah, so really, with this formalism, we also get this restricted statement. So yeah, if I have this analytically generated sharply o-minimal structure like this, so we show that if we have a set in structure with some format and degree, then we get these Wilkie type polylog estimates, and again the dependence is polynomial in the degree of the set you start with, and the polynomial depends only on the format. And sort of what we had to do in order to get this was we had to find an extension to the sharp setting of what's called complex cells. This was a notion introduced by Dmitry a few years ago. And these are the sort of suitable complex domains I alluded to before. And the definition is a bit technical, but roughly we can think of these as these products of disks and handling. And working in this setting, what we do is we prove an effective version of the Yomden-Gromov lemma, and this was sort of the missing piece to get these interpolation by zero sets of polynomials, and this was also what was done in this previous resolution of Wilkie's conjecture. They got some strong enough version of Yomden-Gromov, but actually there they didn't have like the precise original formulation. It was enough to have some weaker version of it, which I won't describe, but we actually get the exact formulation, but also effective. Okay, so this is all I want to say about this restricted case, but now I want to start talking about how we add in the unrestricted exponential. So just a bit of history about just o-minimality of unrestricted exponential. Okay, so the first result in this direction was 91 when Wilkie showed that the structure ℝexp is o-minimal. And yeah, indeed, it didn't just do it directly. It first got some more explicit description of sets in the structure. This is this model completeness property. Then using this more explicit description, we got o-minimality. And later, Dries, McIntyre, and Marker, they showed that also this larger structure Rnx is o-minimal. And again, this followed through by first sort of analyzing and understanding better what are definable sets in the structure. They got something stronger than model completeness. They got that every definable function is piecewise given by what's called terms in a suitable language. But the proofs of both of these facts are model theoretic, so they rely on passing to some non-standard larger models that satisfy the same first-order theory as these structures, and this is sort of very, it's not clear how to effectivize this sort of thing. But a bit after that, Lion Rolin, they gave a proof of this result of Dries, McIntyre, and Marker, and they did it in some more sort of explicit geometric way, and they used what they call logarithmic exponential preparation theorems. So I'll get back to this soon. I'll just say that after this was specifically for Rnx, and Dries and Speissegger, they generalized this to a setting where you replace this Rn part by basically any o-minimal structure. Okay. So questions so far?
I'm sorry, I'm missing something very basic, and I apologize for the question. So, is analytically generated sharp o-minimal, is that a relaxing of sharp? Or
No, it's a
strange
additional assumption.
So it's just the theorem on analytically generated. The asymptotics look the same as in the general.
So in general, we don't have this sort of polylogarithmic result.
I see it. This is only for, so far. This has previously been.
So there's also two cases this is known, right?
There were in our theorem with Benny and Dmitry, there's another assumption about the derivatives called sharp derivatives.
I see.
And here, kind of, if you have analyticity, you don't really have to make assumptions
Okay.
about the higher
Thank you.
derivatives. Sorry.
So in both cases, we need to have something extra. It's not clear how to get this just from this filtration axioms. Yeah, but the idea was that this analytic generation is something you expect to happen in practice. So functions you expect to work with, they come from something homomorphic or neuromorphic. So we're thinking about something like take the structure generated by all restrictions of the gamma function to disks in a complex space. So we don't know this is sharp yet, but it probably won't be with the sharp derivatives, but it would be analytically generated. Okay. Any more questions? Okay.
Actually, sorry, can I ask? But maybe this is related to what you just said. So if you have like a differential equation with regular singularities, so and you want to join solutions so that maybe restricted stuff. So A, do we know that's sharp? B, does it have sharp derivatives? And C, is it analytically generated?
So I think maybe for this singularity stuff.
We don't know it's sharp.
Okay.
I conjecture that it's sharp. We know it's effective. So if you put them, it will be effective, even unrestricted. You can take it in singularity. You can get effective results, but not sharp. And it is kind of analytically generated if you took restricted to holomorphic domain. But if you want to get all solutions, you have to add log, and log is not analytically generated. So you have RLN with you add holomorphic solutions of differential equation, and then you have RLN exp. So just kind of the AN part you can replace by some solutions of differential equations. Then you can add exp, and then you can really recover all solutions of regular singular equations, even around singular.
And maybe you were saying this yesterday, but like the sharp derivatives.
I expect it will have sharp derivatives because you have differential equations, but I don't know how to get sharpness at all. So it's kind of there's not even a question to be asked, but yeah.
So why doesn't the bound on derivatives follow from having anti-continuation? Shouldn't you be able to use something like Cauchy's formula to?
So this is sort of what we do, but this gives us control on the growth of these derivatives, but not on their complexity.
I see.
Yeah, but I mean that's a good question. That's kind of the idea.
So I just say that, yeah, when you add this unrestricted exponential, it can't hope to be analytically generated because it's not analytic at infinity, and this is sort of the difficulty. So even if you look at this sort of this structure here, so some previous work of Gan and Dmitry, they show these polylog counting in this structure, but there, yeah, the result, the methods are also this complex geometric approach, but it's not clear how to get unrestricted exponentials because, yeah, you can't use these exponentials on larger and larger domains without increasing the complexity. And we sort of we split the problem into two parts. There's sort of a real part where we hide all the unrestricted exponentials, and then there's a holomorphic part when we only deal with restricted stuff. So we'll see how this works. So I want to talk about this notion of preparation theorems, like in Lion Rolin's work. So the first of these is what I'll call S preparation. So S is like sub-analytic, but really it's like structural. What I mean by this is just something that lets us take functions definable in their structure and cut up their domain into some pieces, and on each piece we can express them in a nice form. So this nice form is as a unit times a monomial. It's not exactly a monomial. I allow here also these shifts. So for each coordinate function, I can shift it by some function of the previous coordinates, and then I take some power. And by unit, I mean this is a function which has some bounded logarithmic width. I can think it's maybe between 1/2 and 2. And just as a picture for where this looks like, this picture would be simple now, but we'll come back to it later. What I want to say, this is like sort of a local resolution of singularities. You have some function f, and maybe it has some complicated zero set, but you pass through charts where the zero set looks like a normal cosine divisor. It's like the zeros of some monomials. The picture is I have some set A. Have some function f, everything's S, function R. So first what I do is maybe with these shifts, I pass to some domain, and this domain extends to some complex domain. And on this complex cell, I have a holomorphic function that extends my original function f. So this is sort of like a chart where this f becomes monomorphic. We'll get back to this picture later.
You're doing things like blowing up or something. It's not everything is one-to-one here, I assume.
No, yeah, I have to
Yeah,
pull back my coverings and all sorts of things like this. But the idea is that when I do this holomorphic viewpoint, I can get an effective version of these sorts of these propositions. So I mean, I have good control on how many pieces I need, and I have good control of the complexities of these units and of the centers. And also there's like something I can get from this. I'll draw this stuff. If I just want to write a function in this way as a monomial times a unit, there's maybe different ways to do it, and it's not clear what is sort of the correct one. Let's say I have an interval. Now I have the function x squared. I want to write it as some monomial times some unit. Okay, but I can do this in many ways, right? I can take the monomial to be x squared and the unit to be 1. But really I can take the monomial to be x0 and the unit to be x squared, and this, it's not clear what is sort of the correct choice. But if now I don't think of it just on some real domain, it extends maybe to some annulus. and this graph of the function extends to a graph of a holomorphic function, okay, then these exponents, they don't just tell you something about the rate of growth of the function, they also carry some information about variation of arguments. So as I wind around the origin in the domain, the value of the function also winds around the origin, and that tells me sort of what is the correct choice to take here. And this is something I can read off topologically from these continuations. And moreover, I can use this to bound them. I mean, if I want to estimate the size of this winding number, that's like counting intersections with this positive real axis, and doing these sorts of estimates for the size of intersections is exactly what this sharp formalism for. Lets us take care of that track.
So what's the right choice?
So you have to sort of expand the function holomorphically and see what happens, right? So it's not clear if you just have the function and it's written down, it's not clear what you will get, and it's not really canonical in the sense that there is a one right choice for one function. You run this algorithm, you get all these charts covering your original domain, and on each chart you get some expansion and you check the winding there.
Yeah, but once you have a complex cell like this, then it is canonical. It's really just given the monomial is the winding number of the.
You want to take out as much of the homology.
You just check what is the image of.
I see.
You have a map which takes non-zero values, so it defines a map to the fundamental groups, and then the image of the generator is.
This sort of holomorphic viewpoint is also what gives us the bound on the unit. So what's happening here is, let's say I have my sort of real domain and it extends holomorphically to some. I have this real domain, I have a function on this real domain, and it extends holomorphically to some disk. Okay, so actually what's going on is that I only need this disk, but the function actually extends to a much larger disk. You can control the sizes of these extensions. And these sorts of disks or annuli in the complex plane, they have a natural hyperbolic metric. And if I can get this extension to be very large, that says something like this disk inside is hyperbolically very small. And these sorts of things, they let us control the size of this unit. So this unit extends to a holomorphic function, and because of these hyperbolic metric considerations, it can't move much. So this also goes into getting this sort of constant logarithmic with units, which it's not clear otherwise how we will get. Okay, so just I'm restating this. So what we have is, if we have any collection, finite collection of k functions in this analytically generated sharp structure S, then we can indeed cover the domain Rn by a number of cells, which is polynomial in the degrees of the function and the number of functions, and this polynomial depends on the format of the functions. And on each one of these cells, we have this sort of expansion. So for example, I can write it down with respect to the last coordinate. So I have some shift of some function dependent on the previous coordinate to some power. I have something which only depends on the previous coordinate times some unit. And I can then sort of recursively apply this thing to this part which depends on less coordinates to get these monomializations that we had before. And here I want to note that we do this for several functions simultaneously, but we only have one of these sort of centers of expansion. This counts because of this fact that we have one sort of common domain that we pull back all the functions. So,
but so in doing this, like the complex domain doesn't exist a priori, right? You're sort of choosing the cover and choosing which domain you're forming.
Yes, I'm given some real domain and some real functions on it, and now I have to construct these domains.
Okay. And somehow, no matter how you do it, it all ends up being more or less the same story or something.
Yeah.
Okay.
And also these functions, we have control of their complexity, so each one of these participants here, its format is only some function of the format of what I started with, and if degree is also polynomial in the original degrees, and the choice of polynomial depends on the format of what I started. Okay, so much for this restricted S preparation. Maybe just one more thing I say is that this sort of stuff, this sort of theorems in the classical setting are quite useful in application. So these are used in, for example, you want to show you have an analytic family of functions, sub-analytic family of functions, and you want to show that they're the set of parameters where they are integrable is also, let's say, definable in R and X. So this follows from these sorts of preparation theorems, and in fact, it also gives you the integral. So assigning to each one of these points in the base the value of the integral, this is also a function definable in R and X. So we did the same thing, but now we have this more effective control on everything. So it's reasonable to expect that you can now go to the applications of this original sub-analytic preparation and try to effectivize them using this kind of result.
What if you integrate with some weight? I guess it's automatic then as well because it's not a definable function. So do you get definability of some like Fourier transforms or I guess with Fourier it's
yeah, so I'm not sure specifically, but
if you integrate definable sub-analytic function, then yes. If you do Fourier transform, then there are papers about that. But not sure what you get exactly. You get in some kind of class, but maybe not in R.
okay, so we have this sort of S preparation theorem for functions in S, and now I want to think about functions in ℝexp. So first of all, it should be clear that it's not possible to get this sort of same sort of statement or something as simple for these functions because there's more types of asymptotic growth in the structure. Just take the unrestricted exponential. Okay, you won't be able to piecewise express it in this way we had here because on an unrestricted piece it doesn't grow. We have to introduce something else, and a priori it's not even clear that there's any sort of basic set of asymptotic growth types that you can decompose any function into. It's not clear a priori that maybe once you add x, you could get all sorts of crazy things when you take projections and all functions definable in the structure. And these E preparation theorems tell that actually there's also a sort of basic description of all behaviors of definable sets. But now you have to introduce logarithmic growth rates and exponential growth rates. What we get is we get a similar sort of theorem where we take any definable function in the structure and we piecewise decompose it, or we decompose the domain such that on each piece we have an expansion. This function is a unit times a function of less variables like we had before, times a monomial, but now it's not a monomial in the coordinate functions, it's a monomial in terms of something called a log scale or a log_x scale. So what is this sort of thing? This is a sequence of functions, and you construct them in the following way. So you start with this, let's say we have this logarithmic part. You start with L0, so L0 is just some shift of, let's say, the last coordinate function, like we had in this sub-analytic preparation. And now each subsequent term of this scale, you get it from taking the previous term, applying log, and then maybe doing another shift of less variables. So they get sort of more logarithmically nested as you go. There's also an exponential part for this scale, and here the definition is less, sort of less interdependence between these functions, and not each of them defined by the previous one, but there's some finite list of functions, and it's useful to order them in sort of weakly increasing exponential nestedness. So each function has more nested exponentials in its definition than the previous one. When we do this sort of piecewise compositions, we can construct the pieces we work with such that these terms in the scale are no vanishing. So these exponents are, of course, not vanishing. These are real exponents, but I mean, in general, but are not negative. And we can also choose these non-vanishing. So like before, we get a sort of result of this form where we can take a function, it has some complexity, and using this complexity, and with respect to this complexity, we effectively decompose it, the domain, into simple pieces, and in each one of these pieces, we have this sort of expansion. So we have some unit, we have powers in terms of some log scale, we have some exponential term, and then we have a function of just the remaining variables. And we control the complexities of everything appearing in here and the sizes of these exponents. Particularly, what this sort of expansion gives us, it gives us that the sign of this function of n variables is really only determined by the sign of this function of less variables. So all these exponents, units, and these powers, they don't change the sign. And this sort of thing where you have you pass from n variables to n minus 1 variables is what lets us get an effective quantifier elimination result for the structure. So this is something saying like if I start with a set definable with qualities and inequalities of basic functions in my structure, and then I project it down to less variables, I again get something given by equalities and inequalities of basic functions in my structure. And this is sort of a big part of this. And using these effective quantifier elimination results, this is what lets us define the correct choice of FD filtration on this set. So a priori, we have some definable functions here, and we need to decide what it means that a set has some format and degree, and using this decomposition into a small number of pieces, this is what lets us do. So the definition will be something like a set has low format and degree if it's a union of a small number of simple pieces in this decomposition, and each one of these simple pieces has some low syntactic complexity and functions that define it. Something of this sort.
So you need S somehow to have enough stuff in it.
In what sense enough?
Well, if S were just R out, then you couldn't.
So at the very least, yeah, you're right. At the very least, I need this S to have this restricted exponential.
Right.
Otherwise, I can't. Yeah,
Okay.
thank you. That's a good point. So this whole thing I should have written. Okay, so let me make this precise. So for this, we don't need anything, just that it's analytically generated sharp. And once we want to add this unrestricted exponential, we need to have an additional assumption that we start with something that actually has a restricted exponential inside. So for example, this structure here of restricted elementary functions. Okay, so indeed, if we start with this.
However, by the way, it is true, but if you have a sharp structure, you can always add the restricted exponential and it will remain sharp. So, I mean, so you can still get. So it's
In
not-
two steps, you.
Yeah, so just not as a black box like before, but
Is the more general thing true? Can you add restricted Pfaffians for your sharp structure and get something sharp?
Yeah, I mean, I know it's true, it's not written anywhere, but
Secretly true.
it is written for effective. So I have some paper where I did effective things there. I needed this and I wrote it for effective. I think you can do the same thing and it also works for sharp.
but for restricted exponential, this is
It's also not written.
okay. It's the same. It's the same.
Yeah, you should kind of say, okay, it's the Pfaffian
Is it not
closure.
written in the same place?
It's the same paper where that is not written.
Okay, so yeah, after that you could do that in 2 steps, but just for what we have here, yeah, you need to assume something extra.
Can I ask one more question? Sorry.
Yeah.
Do you have an example of something which satisfies this analytically generated assumption or a structure you have in mind? Like, could I throw in like all differential equations or something and hope that's true? Or
Like for solutions of differential equations.
yeah, I don't know. Like, what is the
So this was this.
You mean analytically generated or sharp and analytically generated?
sharp analytically generated, whatever the theorem is?
I have some structure that I call RLN, where you add all like differential equations with logarithmic type singularities, and I conjecture that it is sharp. And
Okay.
it would certainly be also analytically generated because you're just taking solutions of like differential equations. They're always holomorphic.
But somehow the plan is to prove it and
I mean, well, okay, plan is a big word.
okay, but that's okay.
It would be like effectively analytically generated, and
Yeah.
all this stuff would work where you would replace the polynomial dependence on the degree with just effective dependence on some notion of complexity. Let's say you only have a form, something like this. And all of these things should follow through in such a structure effectively, but just as an example that's maybe larger than this, you can start with restricted Pfaffian functions and look at all sort of holomorphic graphs where the real part and the imaginary part are Pfaffian in the real sense, and you can apply it to something like this.
Okay.
Sorry, I think I just lost something. On the previous slide, you had these exp of E1, exp of EE.
Yeah.
How do they appear in the next slide? Like how they?
Okay, so here it's sort of, for this slide, what I only wanted to say is something about the sign. So I have some function of some variables, and its sign is determined by the sign of less variables. So I sort of hid all of these exponentials just in this term. I have these exponentials, they're raised to some powers, that power goes into the exponential, and I can also put everything here. But that's only when I only care about the signs. If I also want to know like something more specific about the structure of the function, I didn't say this before, but here we have this decompositions as powers of these terms and a function of less variables and a unit. And it's actually important that this unit, it's also some specific structure. This is an analytic function of the terms of this scale. So if you sort of combine them together and stick them into one exponential, you lose this sort of information about them that's important because you plug them into the unit.
By the way, a small point of credit is that this thing with the unit is only in Lion Rolin and not in the. There was a later work by Speissegger and others, but they don't get a good expansion for the unit. That's part of why we only know how to integrate some analytic sets and not general polynomially bounded sets, because you don't get this good unit in this preparation.
We sort of recover the explicit description of the units they had in Lion Rolin, but we also do it effectively. So this is how we get sharpness of, so from say this restricted elementary structure, we can add the unrestricted x to it, and ℝexp is a substructure of this. So in particular, we get sharpness of ℝexp in this way. So now I want to say something about the point counting. So the idea is sort of like this drawing I had there before, but now it's different, so I'll just point it out here. So I start with this, I have a function definable in Sx on some domain A, and I want to do this sort of decomposition like before. Before I had these shifts, say I inside the monomials, but now I use this log_exp table. But really, it's not just like what we had in the previous slide. Here we had something corresponding to the last variable, and I need to do this actually for every variable. So I have a scale like this describing the dependence on xm, and a scale for the dependence on xm minus 1. For each one of the coordinates, I have these sort of sequences. I concatenate all of them, and this is what I use to move into a domain in which the remaining part of this function f is driven by something definable in the structure S, something subanalytic, which then extends holomorphically to its larger complex domains, is complex sets. And so right before, these components of these cells, these are like orders of disks and analyte, and each component has some hyperbolic metric on it. And we can choose these holomorphic functions to actually extend to larger disks and larger annuli in such a way that everything in the scale, etc., maybe one term per coordinate, is hyperbolically so small that we can ignore it for all the estimates we need to prove point counting. So we can think here that we have this cell, maybe it's in some, it lives in an ambient space of much larger dimension than what I started with. But because I can ignore most of the terms actually in this log_exp scale, I can think I've landed in something of the same dimension, and then applied some holomorphic math to recover my original Sx definable function. And this is not exactly how we do it in the paper, but morally, what's happening is that we can take these holomorphic maps, we can consider the Taylor expansions, truncate them at the correct place, yeah, and assume these are actually polynomial maps. These cells we can always take to be semi-algebraic. We apply this sort of picture, for example, to just the coordinate functions on a set A. We approximate the coordinate functions by polynomials of some semi-algebraic set. This gives us an approximation of the original set by some semi-algebraic set. It's important for us to be able to do this with the same dimensions. So the result is sort of something like if I have a set in Rn, definable in Sx, and it has some format f in degree d. Let's say I want to approximate it with this Hausdorff distance between sets up to distance epsilon. So I can do that with a semi-algebraic set of the same dimension, and its degree would be at most something polynomial in the original degree, and maybe log of 1 over epsilon, and the polynomial depends on the ns.
Does B contain A?
No, no.
Can I ask you why the hyperbolic metric shows up, and also which hyperbolic metric do you mean?
So there's one hyperbolic metric, like on a disk or an annulus.
Okay.
This is, yeah, let's say you have the upper half plane.
Yep.
It has its own like standard hyperbolic metric. Okay, let's say normalize the curvature. Okay, so there's holomorphic maps from the upper half plane to a disk or to an annulus, and you just push the metric from there. Right, if I have the upper half plane, and I quotient out by translating to the right, let's say, then this sort of region, this is like a punctured disk. So this is the outer boundary of the disk, and this direction is the puncture. And if I do the same thing, but now the action is not translating, it's maybe scaling by some constant, then this is like gluing two of these circular ups, and these don't have the boundary components of some annulus. So this is what I mean by this square annulus has hyperbolic metric, and how this helps us here is the following fact. So I have the cells, these are sort of like, in each coordinate I have either a disk or an annulus, and I have the functions, defined on these sets, and they are holomorphic, but they actually extend to holomorphic functions on larger extensions of these sets. And what I want to do is I want to work with respect to the hyperbolic metric on these larger extensions. Unless I'm working with something and it only happens to extend up to maybe a disk twice as large, and I need something better. So I can maybe cover, let's say, this disk with smaller disks. And each one of these has a much larger extension relative to its size, and then I pull back to these smaller disks. And I can do the same sort of thing with annuli. And the price I pay is I get more sets. This factors into the sizes of these.
Asking a very stupid question. I mean, a priori it goes with the Euclidean metric as well, right? Like, what is it about the hyperbolic metric? Is there a clear fact about it that's useful over some other metric?
Okay, so maybe this was not. I'll say this, and you tell me if this.
Okay, I don't want to slow you down, so if you want to move on.
No, that's fine. I just want to say that for sort of the price you need to pay here to get a better extension. For the same price, you could make this annuli much smaller than a disk, exponentially smaller. And then it is mapping, when you factor through a scale, all the terms except for maybe one per coordinate, they land in these sorts of annuli. So if I just take these extensions large enough, and this doesn't ruin the other bounds that much, I can sort of ignore all of these things. But I'm not sure, maybe that didn't.
Maybe after
Maybe a kind of answer to your question is, suppose you have a unit. So suppose you have a function that's non-vanishing, but if usually you just get it from compactness argument. So okay, it's somehow non-vanishing, but you don't know the bounds. If you want to make things effective, it should really be small logarithmic width. Then suppose you know the function is defined on a disk and it's not vanishing, then it goes from the disk into, the puncture disk. Okay, puncture disk is not hyperbolic, but suppose it's also bounded or something, then it will actually go to hyperbolic space. And then because the disk inside of its extension is of small hyperbolic diameter, you know that the image is going to be of small hyperbolic diameter in the puncture disk.
The important thing that's not in the Euclidean metric is that we have that holomorphic maps are contracting for this hyperbolic metric. Maybe this was the
I see.
salient thing. I'm sorry. Yeah.
So this lets you kind of control things like how much units move and other kinds of things.
Gotcha. You use Schwartz.
Schwarzschild. Yeah. Yeah. Sorry. Thank you.
Think of what you were saying, that it's important that the boundary of a hyperbolic disk is sort of comparable in size to the volume or something like this.
I mean, we are always far from the boundary because he's always taking these extensions. So what matters is like how a disk looks in the twice larger disk. That's very simple, but more complicated is how an annulus looks in the twice larger annulus. And this is kind of complicated, but it's like a long tube. It becomes longer when it's small, and the middle becomes pinched. And all of these things are kind of playing a role.
There's lots of sort of technicalities I'm hiding here, but the idea is that with this hyperbolic metrics, they interact well with holomorphic functions. And even though we have maybe a very long scale and it runs in some complex cell in a high dimension, actually most of the components of this complex cell are hyperbolically very small, or at least their boundary components are hyperbolically very small. And that's what lets us sort of ignore most of the complexity here and get something of the same dimension.
Maybe just one more small comment about your statement there. That this is new even for Rn(exp). So I mean, something similar was done for Rn(pow) by Jonathan and Alex Wilkie and Clackers. It's like the fact that you can take a set and approximate it algebraically in this sense. If you want the error to be epsilon, then you only have to take degree log epsilon. I wouldn't know how to prove it for Rn(exp). Because it doesn't have sharp derivatives, so we can't use Young-Gromov. And so, I mean, it's even if you don't care about sharp o-minimality and you just do it for Rn(exp), then this kind of corollary would follow from this new approach.
Yeah, and then it's just we without this dependence on degree. But now that we have this, and we're also working in a sharp setting, so this sort of approximation is sort of like the first step in a proof of something like Wilkie or Wilkie's conjecture. And now working in the sharp setting, we can continue with the induction really and take these construct interpolations of rational points by these hypersurfaces, and then we intersect with them, and that usually drops the dimension, and we can control the complexity of the intersection, and in that way proceed by induction. And indeed, we get this sort of statement for a set definable in Sx, but it has, let's say the set X has some complexity, then we get Wilkie type estimates for the number of rational points. And I don't remember if I said it at the start, but all of these theorems have also a formulation where you don't just count rational points, you count algebraic points up to some bounded degree G, and all of these things have the same, but we have this sort of algebraic versions as well. I just, for simplicity, didn't put it in the slide. So everywhere I had this sort of bound, you can put also here polynomial in G. So in the degree in G and in log H. Okay, and again, like before, in the special case where we take the structure RRE, we get Wilkie's conjecture for ℝexp, but now, before we have this more uniform description, right? Before we just had a polynomial depending on x of the log height and say the degree of the algebraic point, and now we have this sort of uniform statement. Okay, so I'll stop here. Other questions?
So is RRE, is that basically the smallest structure you could take to
make this argument work? So I have to have at least the exponential to get this sort of scale part of the argument to work. And okay, it's not clear if it's really necessary, but for what we can do now, I really need this sign to be in there too. We think maybe we can sort of, in this holomorphic step, because we only really care about the real part of this holomorphic set in the end, we thought maybe we could get rid of the the signs appearing, but we couldn't do it, so.
Mhm.
For now, yeah, we have to have at least restricted sign and restricted.
Kind of naively, you want to add x, but on a complex board, so you kind of have to add sign as well. So we cannot recover Wilkie's model completeness only for Rx, for instance.
I see.
But we can recover it probably for this RE.
Do you know that this is optimal, or in other words, do you have an example where you can get some explicit formula for the number of transcendental points? Like some set X, which
And so, no, I don't think, these things are always like just upper bounds. It's not such tightly controlled, and in the argument, there's lots of waste. But the important thing for us is this sort of qualitative shape of this bound, and this is what's useful later.
I guess
But certainly log H is optimal.
Right.
That's y equals 2 to the power x.
I guess back when you near the beginning when you said that you can get, or I forget who, sorry, but like Rx you can deduce Wilkie's conjecture essentially formally, I think, from model completeness. So this kind of thing. Yes, right. Okay. So this won't work for an arbitrary like o-minimal structure and a join exp to it, even though it stays o-minimal. You probably don't have this model completeness anymore, right? So if you can get this kind of deduction is special to Rx.
I mean, you need model completeness, and okay, what Oded was showing actually shows that we can get model completeness effectively as well. But I mean, it's very special for X.
So model
This
completeness.
is like a deep theorem of Wilkie. It's not same as o-minimality. I mean, getting model completeness, it's specific to X. There are interesting examples that are not published, so I don't. But I mean, it's probably not true if you fix a different Pfaffian chain.
Yes.
Then I guess it's not model complete.
But I'm thinking specifically about X, if you fix an o-minimal structure and then you adjoin X to it, do you have some sort of relative model completeness where like if you take the previous o-minimal structure as basic parts of your language and then you adjoin X, do you have model completeness?
This will follow from this.
This proves it.
Oh, this does prove
it. I mean, and if you wanted it non-effectively, then Lion and Rolin proved it. So they were kind of giving a geometric version of this Wilkie theorem. This is kind of.
Oh, wow. Oh.
It's just important to say that the sort of questions of model completeness and quantifier elimination, it's not just a question of the structure, but also of a language. So you want sets in some explicit form.
Right.
So, okay, so with respect to the sort of a natural choice of explicit form, yes, this follows from this result. We get something just like quantifier elimination and this. You can get from this sort of model
You can
completeness.
go to the slide where you had this, what Lion and Rolin did. This
Yes.
Maybe let's go. This one or the previous one?
The previous one, I mean, you said that, okay, these guys proved piecewise given by terms, and then like Lion and Rolin gave a geometric proof of this. So this is even stronger than model completeness. It really means that you can, every function you can really write using terms in the language.
Maybe you already said it. So holomorphicity shows up in the Schwartz lemma.
Yeah.
And are there other important places where holomorphicity kind of is used crucially?
So it's used for hyperbolic geometry, and it's also used in a different kind of a different way. It's not hyperbolic geometry in this it's called the Bernstein index, but maybe it's not a very familiar term. So it's kind of relating the growth of a function to the number of its zeros. It's also needed at some point. So it's kind of more like Kobe theorem. So that if you know that the function is p-valent with a fixed p, then you can say something about its derivative, right? So it's this kind of thing also comes in. That's not exactly a hyperbolic restriction. It's more
So the kind of thing I'm imagining is like certain kinds of harmonic functions are also length decrease or something.
you mean can you do something with
Imagine to
harmonic?
like to negatively curved things or something.
I'm not sure. Yeah, it was always holomorphic functions, and we even use a bit more than not just like hyperbolicity. We use some other things about harmonic functions, like Kobe theorem.
But also in this, I didn't write it down, but in this interpolation step at the end, we use Cauchy estimates and things like this. So it's important for us to be able to, to bound the size of, let's say, derivatives, this also comes from this holomorphic viewpoint.
Yeah, but this might work for harmonic functions.
Okay. Other questions? All right, let's think about it again.